In the modern age, we put great faith in the power of computers. We do all sorts of number crunching, all sorts of computations using them, and put great trust in the accuracy of those results. Indeed, all throughout this course, we have been using computers to carry out some rather complicated computations. Now, occasionally, our deep faith in computers gets jittered. For example, we sometimes saw that when we want to have a diagonal matrix, we expect the off-diagonal entries to be exactly equal to 0, but what we got was something like 10 to the power minus 12, 10 to the power minus 16, very close to 0, but not exactly 0. So that reminded us that computers are not exactly computing the quantities that we want them to compute, but they are doing approximate computations. But most of the time that approximation is good enough for us, and we are quite happy to think that computers are actually doing exact computation. But there are moments when this faith is deeply jolted. Take, for example, an email that I received a few years ago from one of your seniors at ISI. It was an audit email about a strange behavior of R. You can try it out for yourself. So here are the main commands. I have possibly slightly changed the various numbers. So it went like this. You start with the array 1 to 100. So if I print X, it is just a list of numbers from 1 to 100. So if I want to print X3, it will be 3. If I print X89, it will be 89. So if you send any I, then X of I will be that I, when I is an integer. What the student did was the following. He did 57 by 41 times 41. So this occurred inside some more complicated computation that he was doing. So effectively, it reduced to computing I like this. So you will expect that I is 57. And indeed, I is equal to 57. No problem about that. So let's see what is the value of xi. And you find that the value of xi turns out to be 56 and not 57 as you would have expected. Well, you will be shocked. Let's just try out x57. Indeed, it is 57. Store the value 57 in a variable j. Try xj. Still it is 57. But when you print I, 57, xi, that is only 56. That's a surprising behavior. You can try it out for yourself. Now this one you can possibly explain easily. I will leave that to you. But sometimes you get very, very weird results. Take this example, which is possibly related to Hilbert, because it involves a matrix called Hilbert's matrix. This matrix is the matrix which is n by n. We shall work with 10 by 10 case. And the ijth entry is 1 divided by I plus j. So reciprocal of I plus j, where I and j both go from 1 to 10. So let's create this matrix. I will create an array 1 to 10 in a variable called tmp, and then I will construct something like an addition table where the ijth entry of the table will be I plus j. Then I will take reciprocal. Now there is a nice function in R called outer which will create such tables for you. So I will write tab, call it tab, and that is outer tmp with tmp, and you combine them with the function plus. So it creates the table, tmp here, tmp there, and the ijth entry will be created by taking tmpi plus tmpj. Now tmpi in our case is just I. So I will get tab. We can print part of tab to satisfy ourselves, say the first 4 by 4 submatrix, and it is indeed as it is expected. For example, if I look at this entry, it is the 3/12th entry, and it is indeed 3 plus 2. Okay, now I need to get its reciprocal, so I'll call that matrix H, It is 1 by tab. So that's a matrix which is a symmetric matrix because I plus j is same as j plus I. Now this matrix also happens to be non-singular. I want to compute its inverse. I will call it hi. So it is solve is the function to compute inverse in R, and that uses our familiar Gauss-Jordan elimination with pivoting. So I write hi equal to solve of h, I get some answer, no error message, so it is indeed non-singular. And then I want to check whether it's a good thing. Well, h is symmetric, you can check that very easily. H minus t of h, that is h minus transpose of h. Let's see what is the maximum absolute entry in this difference. I will try to see max of apps of these, and that is 0, which means that if I take h minus transpose of h, I just get the 0 matrix. Okay, I should also have the same behavior for h inverse, because I know that if a symmetric matrix is non-singular, its inverse must also be symmetric. So I will try the same game. So I replace that line, and instead of h, I work with hi, and I again expect to get 0. Ooh! That is far from 0. We have already seen that when theoretically we are supposed to get 0, sometimes we do get non-zero things. So far we always saw that they were something like 10 to the power minus 16, 10 to the power minus 10. So they were pretty small, and we could live with approximating them with zeros. But you are not going to think that this number, which has 8 digits, is approximately equal to 0. This matrix is far, far from symmetric. So, that gives us really reason to worry about. Do we really trust computers as blindly as we have been doing all throughout this course? Or maybe computers are just nonsense. Computers may give us wrong results because of 3 possible reasons. 1. There is a bug in the program. 2. The algorithm itself uses some approximation, like instead of integrating a function, you are integrating an interpolating polynomial. And 3. The numbers that you are using to compute are not exactly representable inside the computer. It is this last point that we want to investigate in this lecture. Numbers, as we know them, there are infinitely many of them. Real numbers, integers, there are infinitely many of them. However, when we are using a computer is only a finite machine. There are only finitely many numbers that you can store. However, we are working with infinitely many numbers. So somewhere or other, some numbers, in fact infinitely many numbers, cannot be fit inside the computer. So somehow the computer is approximating the numbers when it is storing them inside. And that is one of the main causes why a computer might give you wrong answer. The way a computer represents numbers is very much like the way we modern human beings do it. Ancient Romans used to have different symbols for different numbers. As a result, in order to represent infinitely many numbers, they needed infinitely many symbols. So effectively, they worked with only finitely many numbers. But we modern human beings use what is called positional number system. For that, we first fix a base, a radix. For example, for most computations, we human beings use the base 10. Then we represent any number to the base 10, and for that we need only 10 digits, 0, 1, 2 up to 9. So we have special symbols only for those 10 things. Then we combine only those 10 symbols to produce any other number that we want. Of course, we might need some symbols like plus and minus and a decimal point, but effectively we need only those finitely many symbols to write down any of the infinitely many possible numbers? Well, a computer does the same thing. It also starts by choosing a base or a radix. Typically, most computers use the radix 2, that is, they use binary system. Some computers use other radixes also. Calculators, on the other hand, mostly use the base 10, just like us human beings. Once we choose a radix, say n, then we'll need some way to represent the n digits required for that radix. For example, if I use the base 10, the radix 10, then I need some way to represent 0, 1, 2 up to 9. In every language, we have symbols for these things. In case of a computer, we need some hardware circuitry that can store n different states. If it is a binary machine, in that case we need something which can be in either on position or off position. If we are using some computer which uses a base of 10, then we need a circuit which may be in one of 10 different states. In all our examples here, I shall be using the base 10 so that we can understand the concepts easily. So suppose we have one circuit. Pretend that this is a circuit, this is a basic building block which is capable of storing a digit, either 0 or 1 or 2, etc. up to n, up to 10 in our case. In order to store a number, we need a number of digits. So whenever a computer wants to store a number, it allocates a number of such boxes to store a single number. Let's pretend in our toy computer we have got 4 different boxes, so we can store 4 digits. Now I said that I can store only the digits 0 to 9 in each of these boxes, so there may be 10 to the power 4 patterns that I can create, so I can store only 10 to the power 4 such things. I can of course allow whether something is positive or negative. For that I will need another type of box which stores the sign. Suppose this is a box which stores the sign. So if I write this here, in that case this is plus, and if I put it like this, then it is minus. So I now get 10 to the power 4 times 2, because these may be in 2 states. So somehow I have to map these 2 times 10 to the power 4 patterns to numbers. Now there are a couple of ways to do this. One technique is called fixed point method. In the fixed point method, we group these boxes, 4 boxes in our example, into 2 groups. I might split them in any way. I might put these 2 in one group and these 2 in another group. I might put these 3 in one group and this in another group. I might put all the 4 in one group and 0 many in the other group. But just to illustrate, suppose I split it equally. So I say this is one group and this is another group. Inside I will put my point. I am using base 10, so it is my decimal point. So that is the point. So whenever I want to represent anything, all the things that come before the point are written here. All the things that come after the point are written here. I am allowed to write only 2 things before the points and 2 digits after the point. Now suppose I am trying to represent the number, say 12.34. How do I do it? 12.34, so I have to store the number 1 in this box, the number 2 in this box, the number 3 in this box, and the number 4 in this box. So I have represented the number 12.34. Now if I try to represent the number, say 1.5, how do I do it? Very easy. I store the number 1 and then I put 5 blocks here and I do not put anything. So if I do not put anything, that means 0. So it is 01.50. What happens if I want to represent a number that will need more than 2 digits either on this part or on that part? Simple answer, you can't do that. So if I ask you to store, say 345, The way it will try to do is 345.00. So it will say point is here, it's fixed point representation, point must be here. So you write 3, well, it is just lost, and I should make it plus because it is representing plus so far. 3 lost 4, so I will put 4 things. And 3, 4, 5 you say 2, 3, 4 and 5, 0, 0. But you will say no, that is not 345, it is 45.0. Well, it could not represent it, so it just represented what it could represent. Should it not give some error message for that? Well, ideally it should, but that error message is produced at a very low level. If you are writing the program using machine language or assembly language, something that can talk with the low level hardware, then there is a little flag called the overflow flag, which is set every time you encounter a situation like this. That is, it fitted whatever it could fit. There was something left out. It just marks that something was left out. Not what was left out, something was left out. Just this yes-no flag is set in a CPU register. Unfortunately, languages like C, Java or R or Python, all those high-level languages simply suppress that. There is no way you can access that particular flag from a typical C program. Now, having said that, there are certain versions of C where the compiler is very special. You can actually track that flag and take appropriate actions, but typically then the code will look rather complicated. So that is what is called a fixed point representation. Pretty simple. It is completely characterized by the radix that you are using and the number of boxes that you are using before the point, the number of boxes that you are using after the point. Most standard computers, they use fixed point numbers to store only integers. That is where the point comes at the very end, everything, all the boxes are in one group, they come before the point, and there are no boxes in the second group. There are various data types in C which do this. Int is one of them, long is another, long int is another one. So all these things differ in how many boxes you are spending to store the part before the point. Of course, the computer is using binary expansion, so that is the binary point there. And each of these things will store only 0 or 1. For such a case, you really do not need a special purpose box for storing the sign, because sign is also plus and minus, only two possible states. So you just map 0 to plus and minus and 1 to minus. So you can use the same type of box even to do that. And these boxes, as you know, are called bits, short for binary digits. There are many low-level computers called microcontrollers. The single chip computer is actually a full-fledged computer. It has got a hard drive, that is permanent memory, that it has got RAM, it has got CPU, and you can actually store a computer program in it that will execute when you power it up. You can write a program in C in order to make it work. Now, such microcontrollers usually have only fixed point representation of number inside them. However, most other computers, the big computers that we are used to work with, even the computers that are part of our mobile phones, they allow another type of number representation, and that is called floating point representation of numbers. And here again we start by choosing a base or radix, and then we need some basic circuitry, the boxes, which are capable of storing one single digit. In order to represent one number, we allocate a number of boxes. In our example, I'll allocate 4 such boxes. Now, the way the contents of the boxes are mapped to numbers, that is where it will differ. In this case, we will again split the boxes into 2 parts. Suppose we do it in this way, 3 in one group and 1 in the other group. And we will put our point I will again explain using base 10. So I will call it the decimal point right at the beginning. So I always put it right at the beginning. Here are three things after that, and this I will explain its purpose later. Now suppose I am trying to represent the number 12.3. 12.3. What I will do is I will look at all the digits that I need to write it. They are 1, 2, 3. I will represent them here. So 1, I put 1 here, 2, I put 2 here, and 3, I put 3 here. Now you will say this is not 12.3, this is actually 0.123. The point is in the wrong place. Well, I can bring it here. No, I am not going to do that. That is why it is called floating point representation. The point always floats up to the leftmost point. So the digit after that point must be non-zero unless you are trying to store the number 0 itself. However, this is not the number that I wanted to store. It differs by a factor which is a power of 10 because the position of the point. In this case, I floated it up by 2 places. It was 12.3. I made it 0.123. So I have to multiply this with 10 to the power 2. 10 is my base. In general, if the base is r, the radix is r. In that case, I have to multiply it with r to the power 2. R is already stored in the computer. The computer is built with some specific R in mind, so there is no need to store it separately. I need to store the number 2, and that is precisely where my next group of boxes will come into play. Here I have used a single box in that group. I will put the number 2 in that box. So the representation is 0.123 times 10 to the power 2. This is basically the scientific notation that most scientific calculators use. And when they print it, they will often print it as 0.123 E and then write 2. In scientific calculators, typically they put the point here after one digit, so they will report it as 1.23 E1, but the way it is done inside a computer is it is taken all the way to the very left and then you put the appropriate power in this box. This part is called the mantissa and this part is called the exponent. So the two blocks are mantissa part and the exponent part. Now, suppose I want to represent the number, say 0.0123. What do I do then? 0.0123. I again see that the same digits occur 1, 2, 3. I keep them in this way, but now the point was supposed to be one step more to the left. It is not, so I have to divide it by 10. That is 10 to the power minus 1. So I need to store minus 1 here. So I need something, a box which can store negative. So I will make it in the minus position and I will put only one thing. So this now represents 0.0123. In this way, you can store whatever you can store. If you have 3 digits, you can store them, and this can go from minus 9 to plus 9. What happens if you cannot fit a number within these boxes? Then something interesting starts to happen. What the computer will do is the following. If this box overflows, for example, you are trying to represent the number, say 123. Then again you write 1, 2, 3, but now you need to multiply. 123 will not have any problem. It is 10 to the power only 3. But suppose you want to write 123 into 10 to the power 100. Then of course you need to store there 103. In order to write 123, I already have to put 3 here, and then 100, I have to write more digits. This box overflows. The moment this box starts to overflow, then we call it floating overflow. And the computer will write infinity. So it has a special representation, and that is infinity. So it will print inf in case of R. And similarly, if you have a negative sign over here and then this box overflows, it will print minus infinity. So anything that is larger, because this box overflow, will give rise to infinity or minus infinity. Now suppose this part overflows. Suppose you want to write 0.1234. So the point is here 0.1, 2, 3. There is no box to store that 4. So what we will do is we will just now store it. And this will be 0. I am writing 0.1234. So what is being written is 0.123. That 4 is completely ignored. And that is precisely where all the approximation enters into the picture. That number is stored approximately. So what it will do is that it will store only the significant digits. What is meant by significant digit? When I give you a number, you look at the first, you look at its expansion, say the decimal expansion. So it's a sequence of digits, possibly an infinite sequence of digits. And then in this infinite sequence of digits, you look at the first non-zero digit. If the number is entirely 0, then there is no non-zero digit. If it is non-zero number, look at the first non-zero digit. And that is called the first significant digit. You keep on following that digit until you come to the last non-zero digit. Everything after that is 0. This sequence, all these digits in between are called significant digits. There may be 0 things here also, but they are always sandwiched between the first non-zero digit and the last non-zero digit. It is quite possible there is no last non-zero digit. For example, if you are trying to represent 1/3 in decimal system, it will be a recurring decimal, 33333 goes on. Or if you want to represent √2 or an irrational number, it will be a non-terminating decimal expansion. In that case, starting with the first non-zero digit, everything after that are significant digits. So what this floating point representation does is, it just stores a number of initial significant digits. In this system, it stores 3 significant digits and simply chops off, no rounding anything, it just chops off, cuts off whatever comes after that. And that is where approximation enters into the picture. If this overflows, then there is at least some way you can give some message. Oh, I forgot to mention what happens if this overflows in the negative direction. So it is 10 to the power minus a very large power and it cannot store it. Then it approximates it using 0. And that is why computers will always tell you 1/0 is infinite, because for it 0 means something very close to 0. So if you take its reciprocal, you are likely to get something enormously large. So many systems actually distinguish between -0 and +0s. -0 means very close to 0 from the negative side, and +0 means very close to 0 from the positive side. So depending on what system you are using, you will have -0 and +0. So if you take 1/infinity, this means you are taking a very large number, something that caused this to overflow. You take reciprocal, so you get some very small number which will again cause this exponent to overflow in the negative direction, and that is what is 0. So both the fixed point and the floating point system involves approximation. And that is natural because both the systems are working in a finite machine and they cannot represent infinitely many numbers. So some kind of approximation must be there. In case of fixed point system, this approximation is very simple, pretty straightforward. You know how many decimal points or how many decimal places or how many binary places you are going to store, and all the numbers that may be represented exactly are equispaced. For instance, for integers, they are equispaced at 1. And there is the smallest number and there is the largest number that you can represent. Everything beyond that will cause problem. And typically these two ends are pretty huge, something like 2 to the power 31, 2 to the power 32, something like that. So they are huge numbers. you will rarely cross those boundaries. And if you believe that your computation might occasionally cross those boundaries, you can keep appropriate check. So they are sort of extreme situations, and you will know if your program is meant to handle those extreme situations. For day-to-day work, you will usually just pretend that they can represent all the way up to infinity. You know you are never going to go that high. However, the situation is quite different in case of floating point numbers. First of all, they cover a much wider range, and the points that can be exactly represented, they are not equispaced anymore. Thanks to those power system, they are actually spread out, something like a geometric thing. The numbers close to 0 that may be represented exactly are very tightly together. You can represent numbers like 00001, 00001, 00001 and things like that simply by cranking up and down that exponent thing. The numbers that are lying far out, they are again spaced at enormous powers of 10. Like every time you crank it up, something like 10 to the power 30, 10 to the power 31, 10 to the power 32. So all the numbers are spaced far apart. So you are covering a much larger span at a non-uniform intervals. And the numbers in between are all approximately represented, and this approximation is pretty tricky because you are looking at number of significant digits and then keeping only the most important significant digits and chopping off the rest, so the degree of approximation keeps on varying. So that is somewhat difficult to keep track of. So floating point system has the great advantage of being able to handle a much wider range of numbers, but the type of inaccuracy that it introduces is much more difficult to understand intuitively. It is unlike the fixed point system, where if you know that there are 2 decimal places being kept track of, whenever you see anything that has got more than 2 decimal places, you immediately know that it is going to be approximated, and the approximation is going to be the first 2 decimal places will be correct and the things after that will be incorrect. Simple rule. No such simple rule for floating point numbers. Let us take a closer look at approximations introduced by the floating point number system. There are 2 aspects to it. One is called loss of significant digits, and the other is called introduction of trash digits. And these are sort of opposite to each other. We had a number of boxes to store the significant digits, the mantissa part. I will of course assume for the time being that my exponent part is not overflowing. We do not have what is called a floating overflow or a floating underflow. That means that exponent part is actually causing problem. I assume that we do not have that problem. So you can actually represent the number without going in too close to 0 or too far out towards infinity. Then you look at only the mantissa part. There are a number of boxes. Say we take 3 boxes. But the number that you are trying to represent has more than 3 significant digits. Then you cannot store all of them. You have to keep only the most significant, that is the ones which are come nearest to that decimal point. You will keep only those 3 and ignore the rest. That is quite naturally called loss of significant digits. A more subtler thing occurs when you have less number of significant digits than you have boxes. You might be wondering, why should that give an error? We have more boxes than is necessary, so we will just put zeros in those boxes. So why should that introduce any kind of error? Well, there is a rather subtle reason why that introduces an error. In order to understand this, suppose we are trying to measure a length using a scale. Now when I measure something using a scale, and my scale is marked in centimeters, and I measure something which turns out to be 2 centimeters and going slightly beyond that 3 millimeter mark after that, I will call it 2.3 centimeters. To be precise, I will call it 2.3 centimeter up to the nearest millimeter. Now when I say this, I am basically also giving an idea about the precision of measurement, not merely quoting a single point. I am basically giving an interval. If on the other hand I say that the measurement is 2.30, that typically signifies that I measured up to 0.01 centimeter. That is why I am saying that it is 2.30. Mathematically, 2.3 is same as 2.30, same as 2.30000, but when we quote a number, we have this understanding that we are not mentioning numbers that we have not measured. I have only measured it up to a millimeter, then I will call it 2.3 centimeter. However, when you are using a computer, say floating point representation, you have a number of boxes in the mantissa, and each of these boxes must be in some state. They are just circuits. They must have some state, and they can have state 0, 1, 2 up to 9 in case of base 10 example. If you say I do not put anything there, by default they are 0. Empty boxes means 0. So when you want to write 2.3, you end up writing 2.3000. How many zeros? As many zeros as you need to fill up all the mantissa boxes. That does not mean those zeros have any meaning. You should ideally say I do not know, I do not know, I do not know in each of those boxes. But you are writing 0, 0, 0, 0 as if you know that they are zeros. These things are called trash digits. Trash digits need not always be zeros. For example, suppose you have this 2.3000 and now you have to divide it by 2. What will you get? You will get 1.15. Had it been exactly 2.3, you will get 1.15. This 5 will possibly get mixed up with whatever was supposed to come after that. You really did not know what was going to come after that. 2.3, then things were unknown. So this unknown thing would actually mess up this 5. So you really cannot put much faith in this 5 either. But when you do this division in a computer, it will report exactly 1.15000. So this 5 will also be a trash digit. So it is non-zero, it is a trash digit. And we have seen trash digits all along in our course. Every time we expected an answer to be 0, but we found that it is something like 0.00000, etc., etc. We were actually looking at trash digits. So loss of significant digits and introduction of trash digits are two ways this finite precision floating point representation might garble up our actual computation.